Hello student, welcome to your chemistry lab. Today I am discussing reaction mechanism part 3 of organic chemistry. Today I will discussing free radical substitution reaction. We know that about free radical. I had discussed in GOC, that means General Organic Chemistry part 1. You are watch this video for clearing of free radical. So you must watch for clearing about free radical. So we are start today. Now you are watching the whiteboard. Hello student. Free radical substitution reaction. What is radical? A radical is a reactive intermediate with a single unpaired electron formed by homolytic or homolysis of a covalent bond. Means homolytic cleavage form a single electron of covalent bond. Here AB is a covalent bond or covalent compound from A dot and B dot, that is radical. A radical contain an atom does not have an octet of electron, making it reactive and unstable. Radical possess involve single electron, so half-head arrow means half-head arrow are used to show the movement of an electron. One half head arrow is used for each electron. And next, carbon radical are classified as a primary 1 degree, secondary or 2 degree, and tertiary or 3 degree by number of R group, that is the alkyl group, bonded to carbon with the unpaired electron. A carbon radical is sp2 hybridized and trigonal planar. Like sp2 hybridized carbocation, you see that structure of carbocation and hybridization of carbocation, you know that. The unhybridized p orbital contain unpaired electron and extended above and below the trigonal planar carbon. See this picture. Here angle is 120 degree because structure is trigonal planar and sp2 hybridized and p orbital contain single electron. And next, production of radical. Energy in the form of heat or light must be supplied to cause the homolysis of covalent bond. Here heat or light, here light is UV light or sunlight, that is the H nu. For example, compound with an oxygen-oxygen single bond called peroxide undergo homolysis readily when heated. Because OO bond is weak, the product are two radical called alkoxyl radical. Here reaction are given. Here dialkyl peroxide homolysis from alkoxyl radical, that is RO dot RO dot. And next, halogen molecule also contain a relatively weak bond. Halogen undergo homolysis readily when heated or when irradiated, that is the UV light, that is the sunlight that can absorb by halogen molecule, and from given reaction are given here XX from X dot in presence of UV light, sunlight or heat. And the product of this homolysis are halogen atom, because halogen atom contain unpaired electron, they are radical. And next, homolytic bond dissociation energy. Bond dissociation energy for cleavage of CH bond are used as a measure of radical stability. For example, two different radical can be formed by the cleavage of CH bond in CH3, CH2, CH3. Here given energy form, first 1 degree, Here hydrogen is cleavage and form 1 degree radical, and that del H value is 410 kilojoule per mole, and 2 degree hydrogen and form 2 degree radical. Here del H value is 397 kilojoule per mole. Cleavage of the stronger 1 degree CH bond to form 1 degree radical, that is CH3 CH2 CH2 dot, require more energy than the cleavage of weaker 2 degree CH bond to form 2 degree radical, that is CH3 CH dot CH3, and this makes the 2 degree radical are more stable because less energy required to its formation. Thus the cleavage of weaker bond form more stable radical. And next, the stability of the radical increases as the number of alkyl group bonded to the radical carbon increases. That is, CH3 group increase means plus I effect, that is inductive effect increases. So more inductive effect group, that is methyl group or alkyl group, form a more stable radical, just like a carbocation, just like a stability of carbocation. Here also same, CH3 methyl less than RCH2 1 degree radical, R2CH 2 degree radical, R3C 3 degree radical. Increasing alkyl group substitution, increasing alkyl substitution, increasing radical stability. Thus 3 degree radical is more stable than 2 degree radical, and 2 degree radical is more stable than a 1 degree radical. Increasing alkyl substitution increases radical stability. In the same way, it increases carbocation stability. Alkyl group are more polarized than hydrogen atom, so they can more easily donate electron density to electron deficient carbon radical, thus increasing stability. Unlike carbocation, however, less stable radical generally do not rearrange to form more stable radical. This difference can be used to be distinguished between reaction involving radical intermediate and those involving carbocation inversion. Reaction of alkane with halogen. In the presence of light or heat, alkane react with halogen to form alkyl halide. Halogenation is a radical substitution reaction because halogen atom X replaces a hydrogen via mechanism that involves radical intermediate. Here general reaction are showing that here X2 is chlorine or bromine, and presence of H nu or heat form a alkyl radical and form HX. Halogenation of alkanes is useful only with chlorine and bromine. Reaction with fluorine is too violent, that is explosive, and reaction with iodine is too slow to be useful. With an alkane that a more than one type of hydrogen atom, a mixture of alkyl halide may result. That is, here cyclohexane plus Br2H nu form bromocyclohexane plus HBr, and propane plus Cl2 form 1 chloropropane and 2 chloropropane. Here observed percentage is 1:1. So next, mechanism of halogenation. Unlike nucleophilic substitution, which proceed by two different mechanisms depending on starting material and reagent, all halogen reaction of alkane, regardless of the halogen and alkane used, proceed by the same mechanism. Three facts about halogenation suggest that the mechanism involves radical, not ionic intermediate. First fact, light, heat or added peroxide is necessary for the reaction. Why? Light or heat provides the energy needed for homolytic cleavage to form radical. Breaking of weak OO bond, that is oxygen bond of peroxide, initiates radical reaction as well. Second fact, O2 inhibits the reaction cause the diradical O2 remove radical from a reaction mixture, thus preventing the reaction. Third fact, no rearrangement are observed. Radical explanation, radical do not rearrange just like carbocation. Radical intermediate state are not rearranged. The chlorination of cyclopentane. Cyclopentane react with Cl2 in presence of heat and light from chlorocyclopentane plus HCl. And mechanism. First step, chain initiation. Here Cl2, here Cl bond is weak bond and presence of sunlight or UV light form a chlorine radical, that is Cl dot. Step 2, chain propagation. Here first Cl dot, that is chlorine radical, abstract a hydrogen from cyclopentane to form HCl and form cyclopentyl radical, that is carbon radical. And next step, carbon radical, that is cyclopentyl radical, react with Cl2 form chlorocyclopentane and Cl dot. Step 3, chain termination. Here Cl radical, that is Cl dot form a Cl2 and cyclopentyl radical plus Cl radical forms chlorocyclopentane and two cyclopentyl radical form a bicyclo. Termination step 3a forms Cl2, a reactant, whereas step 3b form a chlorocyclopentane, one of the reactant product, and termination step 3c form A, which is neither a reactant nor desired product. The formation of small quantity of A, however, is evidence of the radicals are formed in the reaction. Most important step of the radical halogenation are those that lead to the product formation, the propagation step. So subsequent discussion of this reaction, concentration of this step only. And next, chlorination of methane. Methane first react with Cl2H form methyl chloride and next react with Cl2H form dichloromethane and next chloroform and next carbon tetrachloride. It is a chain reaction. So here number of hydrogen is 4 and hydrogen replaced by chlorine form a carbon tetrachloride. And then chlorination of other alkanes. The chlorination of propane, that is CH3 CH2 CH3, afford a 1:1 mixture of CH3 CH2 CH2Cl and form a removal of a 1 degree hydrogen and next form CH3 whole 3 CHCl form removal of 2 degree hydrogen. Reaction are given and first 1 degree hydrogen, that is the 6 1 degree hydrogen in 1 chloropropane and 2 degree hydrogen in 2 chloropropane, and expected ratio is 3:1 and observed ratio is 1:1 and 1 chloropropane is less product and 2 chloropropane is major product. Here CH3 CH2 CH2 CH3 has 6 1 degree hydrogen atom and only 2 degree hydrogen, so expected product ratio of CH3 CH2 CH2Cl to CH3 whole 2 CHCl, assuming all hydrogen are equal reactive, is 3:1 because the observed ratio is 1:1. However, 2 degree CH bond must be more reactive, and that is it must be easier to homolytically cleave of 2 degree CH bond than the 1 degree CH bond. So 2 degree CH bond is weak bond and less energy required to break and form more stable 2 degree radical. So next, chlorination versus bromination. Although alkane undergo radical substitution reaction both Cl2 and Br2, chlorination and bromination exhibit two important difference. First, chlorination is faster than bromination. Second, although chlorination is unselective, yielding a mixture of product, bromination is often selective, yielding one major product. And next, for example, propane react with rapidly with Cl2 to form 1:1 mixture of 1 degree and 2 degree alkyl chloride. On the other hand, propane react with Br2 much more slowly from 99% CH3 whole to CHBr, that is 2 bromopropane, and reaction are given, and chlorination is fast and unselective and bromination is slow and selective. And next, the stereochemistry of halogenation reaction. The stereochemistry of reaction product depends on whether the reaction occur at stereogenic center, that is the chiral center or asymmetric center, or at another atom with either a new stereogenic center is formed. The rule predicting the stereochemistry of reaction product are starting material, that is achiral, and achiral starting material is always gives either an achiral or racemic mixture, and chiral starting material, if a reaction does not occur at stereogenic center, the configuration at a stereogenic center is written in the product. Point 2, if a reaction occur at stereogenic center, we must know the mechanism to predict the stereochemistry of the product. And next, halogenation of an chiral starting material. Halogenation of the achiral starting material CH3, CH2, CH2, CH3 form two constitutional isomer by replacement of either 1 degree or 2 degree hydrogen, and reaction are given. Butane react with Cl2 in presence of H nu and heat from 1 chlorobutane and 2 chlorobutane. 2 chlorobutane have a stereogenic center or asymmetric center, form two isomer, that is the enantiomer. 1 chlorobutane has no stereogenic center, so it is achiral compound. 2 chlorobutane has a new stereogenic center, so an equal amount of 2 enantiomer must form a racemic mixture. A racemic mixture result when new stereogenic center is formed because first propagation step generated a planar sp2 hybridized radical, and next Cl2 then react with planar radical from either front or backside, front and backside, to form a equal amount of 2 enantiomer, and reaction are given. Here butane react with Cl dot form planar radical, and Cl2 react with planar radical on backside and front side. Front side attack from R2 chlorobutane and backside attack from S2 chlorobutane. Thus the achiral starting material butane form an achiral product, that is 1 chlorobutane, and a racemic mixture of 2 enantiomer, that is R and S2 chlorobutane. And next, halogenation of chiral starting material. Let's now examine chlorination of chiral starting material R2-bromobutane at C2 and C3 position, and reaction are given. R2-bromobutane first react with Cl dot form planar achiral radical, and planar achiral radical react with Cl2 form enantiomer. Front side attack are given and back side are attack given. And chlorination at C2 occur at the stereogenic center. Here C2 carbon is represent, and abstraction of a hydrogen atom at C2 form a trigonal planar sp2 hybridized radical that is now achiral. This achiral radical then react with Cl2 from either side from a new stereogenic center, resulting is an equal amount of 2 enantiomer or racemic mixture. Chlorination at C3 does not occur at stereogenic center, but it form a new stereogenic center because no bond is broken to the stereogenic center at C2. Its configuration is retained and during the reaction. Abstraction of hydrogen atom at C3 form a trigonal planar sp2 hybridized radical that still contain this stereogenic center. Reaction of the radical with Cl2 from either side from a new stereogenic center. So the product have two stereogenic center. The configuration at C2 is the same in both compound, but configuration at C3 is different, making them distereoisomer. So reaction are given. R2-bromobutane react with Cl dot from that product. The configuration at C2 is written, and next Cl2 is react from backside attack and front side attack, and these product are distereoisomer. Thus 4 isomers are formed by the chlorination of R2-bromobutane at C3 and C2 carbon. Attacked at the stereogenic center, C2 gives a product with one stereogenic center, resulting a mixture of enantiomer, and attacked C3 from a new stereogenic center, giving a mixture a distereoisomer. One is enantiomer and next is distereoisomer. So next, allylic substitution or allylic radical. What is allylic radical? We know that an atom or group that is bonded to an sp3 hybridized carbon atom to an alkene double bond is called an allylic group. That means when carbon is attached with cc double bond, that is sp2 carbon, that is cc double bond, and this attached carbon is called allylic or allylic position. So here given example are showing, and allylic hydrogen is specially reactive in radical substitution reaction. We know we can synthesize allylic halide by substitution of allylic hydrogen. For example, when propene react with bromine or chlorine at high temperature or under radical condition where the concentration of halogen is small, the result is allylic substitution and reaction. Propene react with X2 high temperature and low concentration of X2 form allylic halide. At high temperature or presence of radical initiator and low concentration of X2, a substitution reaction occur. Allylic chlorination, that is high temperature. Propene undergo allylic chlorination when propene and chlorine react in the gaseous phase at 400 degree centigrade. Reaction are propene react with Cl2 400 degree centigrade gaseous phase form a 3-chloropropene, that is allyl radical. Mechanism: step 1, chain initiation. Here Cl2, that is chlorine, break ClCl bond and form a chlorine radical Cl dot. Step 2, chain propagation. Here chlorine dot react with allylic carbon of hydrogen, form a allyl radical, and allyl radical react with Cl2 form allyl chloride. And next B, allylic bromination with N-bromosuccinimide, low concentration of Br2. Propene undergo allylic bromination when it treated with N-bromosuccinimide, that is NBS in the presence of peroxide or light. And reaction are given here. N-bromosuccinimide structure have here N attached with nitrogen attached with bromine, so it is short form is NBS, and in exam it gives NBS, not in structure form. So here form a 3-bromopropene, that is allyl bromine. And next, benzylic substitution and benzylic radical. An atom or group bonded to an sp3 hybridized carbon adjacent to a benzene ring is called benzylic group. The group is said to be bonded at the benzylic position, and that means when carbon attached with directly benzene ring, and this carbon attached carbon is called benzylic position or benzylic carbon, and given example are showing. So next, when methyl benzene, that is toluene, react with N-bromosuccinimide in the presence of light, for example the major product is benzyl bromide. N-bromosuccinimide furnish a low concentration of beer. Reaction are given, that is the benzyl bromide. And next, benzylic chlorination of methyl benzene, that is toluene, take place in gaseous phase, that is 400 degree to 600 degree centigrade, or in the presence of UV light. When an excess chlorine is used, the multiple chlorination of side chain occur. That is first reaction given here, toluene, that is Cl2H form benzyl chloride, and next form a dichloromethyl chloride benzene, and next trichloromethyl benzene. I think you are enjoying to watch my video. I think you are understanding the free radical substitution reaction and also clear all the point. If are not clear, so comment me, and I will be replied you, and I clearing your problem. So I will be coming with the next part of reaction mechanism of organic chemistry, that is aromatic electrophilic substitution reaction. So thank you everyone, take care and bye bye.